Okay, I'll go ahead and get started. Just a reminder to begin with where we're going, where we're traveling over the next few weeks of classes to the end of semester. We discovered that light was electromagnetic. Light is a feature of the dimension of charge. Over the next weeks, we're going to be exploring the properties of light. We're going to be looking at reflection, refraction. We've been doing that. We're going to be looking at interference, diffraction. We will be doing that. These are some of the fascinating properties of light that we harness and tame in our everyday technological worlds. We'll also discover how light can illuminate the nature of space and time, the true nature of space and time. We'll make some interesting and strange discoveries there. Also, light can illuminate the nature of matter. We're going to discover some strange and interesting properties there too. So the whole rest of the class, we moved on from electricity and the force of electricity. We moved on from magnetism, the force of magnetism. We moved on to light and the properties of light and what it can tell us about space, time, matter. Okay. More specifically, this is the content for today's class. We're going to talk about images that are formed by refraction. Last Thursday was images formed by reflection. We're going to talk about images that are formed by a single refraction, a single bending of the light ray's direction in a planar or a flat interface between two different media. So that's the first bullet here. We're also going to talk about images that are formed by lenses, which involves two refractions, a pair of refractions, as the light goes into and out of the lens. So we're going to talk about images formed by double refraction. As we do these two cases, as we do these two examples, we'll make some comparisons to mirrors, because a lot of what we do today in today's class is similar to what we found in mirrors, but there are some differences between lenses and mirrors that we should point out. So I'll try and do that. Again, this understanding of mirrors and lenses, of reflection and refraction, was literally the birth of modern astronomy. With the development of telescopes, was literally the birth of modern biology with the development of microscopes. Okay, wow. Everything in today's class is based on the law of refraction. Remember, refraction is the bending of light rays when light travels from one optical medium to a second optical medium. So it might be from air to water, air to glass, air to diamond, so on and so forth. So that's refraction, and the whole class is built on refraction, and it's built on the law of refraction. So I just wanted to remind us of the law of refraction. Here it is. Here's a picture of it. Here comes the incoming ray, what we call the incident ray, at angle theta I. Here goes the exiting ray, what we call the refracted ray, at angle theta R. And here you see these two angles are different. This light ray got bent. It got bent in accord with the law of refraction, which I wrote down here. It's a relationship between the two angles of the incident and outgoing rays and the two refractive indices of the two different media here. Here's a really interesting thing about the law of refraction. I can literally remember when I first heard this, and I sort of couldn't believe it. There was something about it I couldn't believe. So lifeguards know the law of refraction. Every lifeguard knows the law of refraction. And I want to explain why that is. Okay, so here comes this ray heading inwards to the boundary between the two different media, and here's the outgoing ray. And you see in this case here, the refractive index of the upper medium, N1, is smaller. Maybe that's air. The refractive index of the lower medium is larger. Maybe that's glass, because the light ray is bent towards the refractive index. The light ray takes the fastest time, the light ray takes the shortest time to get from point P to point Q. So Snell's law, this law here, is equivalent. It specifies the shortest time, the path that takes the shortest time to get from P to Q. Now notice, not a straight line. That would be the shortest distance. But the light ray doesn't take the shortest path, the shortest distance from P to Q. It actually takes, according to Snell's law, the shortest time from P to Q. And that's actually what lifeguards do. Imagine I was a lifeguard. Imagine I'm in Baywatch. I'm a lifeguard, I'm in Baywatch, I've got to rescue somebody who's in the ocean. If I'm going to rescue somebody in the ocean, well, firstly, I've got to get across the beach. So I'm going to run across the beach. I know this is hard to imagine. I'm going to run across the beach, and then I'm going to start swimming in the ocean out to rescue this person. Should I just run and then swim in a straight line, the shortest path? Would that make sense? No, every lifeguard will know that that's not the right way to rescue the person. Every lifeguard can still, they're good swimmers, but they can run faster on the beach than they can swim in the ocean. Just like this light ray can travel faster in air than it can travel in the glass. So the right way, the quickest way to get to the drowning person is actually to take a longer path on the beach where you can run fast, travel fast, so that you can take a shorter path in the water where you swim slower. And so this is exactly the path that a lifeguard would take from P to Q to rescue a person at Q when they're sitting at, originally sitting at P. And that's exactly what light does. Light travels the shortest path, the path that corresponds to the shortest time between these 2 points. It's not the shortest distance, but it's the shortest time between these 2 points. Okay. Having said all that, let's go on and use the law of refraction. Let's deploy the law of refraction for refraction at a single boundary. That's what I'm going to do first, and it's going to be a flat surface, and then diffraction at a lens, which is double diffraction at the front and back faces of the lens. Okay. Here's an example, here's an illustration of refraction at a single flat surface. Over here on the right, in this picture, is where the light is originating. So it's originating on the right, and it's traveling to over here on the left. That's where the light is heading to. Over here on the right, in my example, in blue, that's water. So imagining there's some water over here on the right-hand side, and then over here on the left-hand side is some air. So this is kind of like a fish tank, right? And I'm looking in the fish tank, something like that. And the light is emerging from some object, maybe the fish in the fish tank. Here is that object. We've indicated a little vertical arrow like we did in the last class. And the light is emerging from that fish, that object. The light rays head out from the right-hand side towards the left-hand side, where I'm going to observe them on the left-hand side. Here's my giant eye that's connected to my giant brain that's going to interpret all this. And we're going to trace some light rays. And we're going to figure out that actually the image that I reconstruct of this object, the image of the fish reconstructed of this fish object, is going to be located here in magenta. And so that's what I just want to show you. And this is just done by ray tracing, the ray tracing that we did in the last class, that we introduced in the last class. So let's see how it works. Just to label everything, here's the optical axis, this horizontal red line. So that's going through the center of the boundary between these two different media. So right angles to that. Here in green is the object position. Here in magenta is the image position. Those positions with respect to where the optical axis intersects the boundary between the two optical media are labeled by P for the object position, like we did in the last class, and Q for the image position, like we did in the last class. The heights I've labeled, the image and object heights I've labeled as the H and H prime, like we did in the last class. So all that's the same. In this particular class, with lenses and refraction, we're going to have different optical properties of different materials. Here I've got air and water, so I've got their two refractive indices. N1 is the label I gave to the water where the light starts, and N2 is the label I've given to the refractive index of the air where the light is going to. Adding to this picture, I've drawn two rays. I traced two rays that allow me to construct the image position knowing the object position. Allow me to construct the location of the image of the fish knowing the position of the fish itself. The two rays that I used are this horizontal ray here in black, and then this angled ray here also in black. And I drew those rays as emerging from maybe this is the fin of the fish or the shark in the fish tank. I drawn those rays emerging from that point. This one, horizontal one's easy to draw. It was heading parallel to the optical axis, so it strikes the boundary at incident angle of 0 degrees. Theta I is 0 degrees. Special cases, Snell's law of refraction, it will emerge from the boundary also at 0 degrees. So embedded in the law of refraction is if you strike at 0 degrees, you are actually undeflected, you emerge at 0 degrees. So here's that light ray, it's easy to draw. And then here I've drawn a second one. This one strikes the boundary between water and air at some angle that's not 0 degrees, maybe this is 20 degrees, it's going to be deflected or refracted or bent according to Snell's law. And because it's traveling from higher refractive index to lower refractive index, Snell's law tells us it's actually bent away from the optical axis. So you see that this refracted angle is bigger than this incident angle. So that's how I drew those two rays, and I hope that's fine. That's just ray tracing that we met in previous classes. My giant eye collects these rays, and of course lots of other rays. And my giant brain analyzes these rays and lots of other rays and says, where are they all coming from? Because that's where the image, that's where I interpret the image to be. Well, let's trace this ray back. It's coming from, if I trace this ray back here, it appears to be coming from this direction, this dashed line here. If I trace this horizontal ray back, it's coming from this horizontal direction here, this dashed line. These two dashed lines, which are me tracing the rays back into the fish tank, come from a common point that's here. This is the location of the image. So this is where the image sits. It's the intersection of those two rays that I trace back from my brain, through my eyes, to the fish tank. Okay. Well, that's how you can sketch, reconstruct in a diagram, in a picture, where the image is located and the properties of the image based on ray tracing. A couple of the properties are that if you look here, the image is the same size as the object. Its magnification is 1. It's not made any bigger or smaller. So that's an important characteristic of single refraction in a flat surface. Also, the image, if you look at it, is closer than the object is to the eye or to the boundary. So that's another important property. That's an important property that's when light travels from higher to lower refractive index, the image is going to appear closer. So this is from water to air. So that is higher to lower refractive index. The image appears closer. So the fish appears closer. The fish is looking at you. When the fish looks at you, the fish sees light traveling from air to water. That's from lower to higher refractive index. The fish will actually see you as further away. So that's, if light goes in the other direction, from lower to higher refractive index, then the image is further away than the object. Okay. We can write down a couple of equations that are handy and describe this situation and quantify this situation. There are these two equations here. So this equation here is an equation for the image position, the upper one, and this one is for the magnification of the image. So the image position is equal to the object position times this ratio of the two refractive indices. So this is the ratio that makes the image closer if the refractive index of the second medium is smaller than the first medium. It makes the image further away if the refractive index of the second medium, N2, is bigger than the refractive index of the first medium. So this is quantifying what I said about the fish looks closer to me, but when the fish looks at me, I look further away from the fish. Let me say something about the signs. There's a minus sign here which brings up this whole topic of the signs of P's and Q's, like that was important also for mirrors, the signs of the P's and Q's. Things are a bit different here for refraction than they are for mirrors, because in mirrors, light always exists on the front side of the mirror, right? And the light is never actually on the back side of the mirror. But in lenses, light exists both on the front and the back side of the lens, because the light arrives at the lens and travels through the lens from one side to the other side. This is what we call the front side. It's where the light originates from. This is what we call on the left here the back side. That's where the light is heading towards. So that's what we mean by front and back. If the object position is on this front side, then that's a positive object position. P is positive. And so that's defining, P being positive means that object is on this side, is where the light originates from. Q being positive, on the other hand, is Q is positive if it's on the back side, where the light is heading to. Now our image is actually still on the front side. So this would be a negative value of Q, and that's explained in this equation by the negative sign here. The other equation is just the magnification. We said that the magnification, if you get refracted at a single flat surface, the image is no bigger or smaller than the object. Magnification is just 1. It doesn't really matter where the object was, where the image appears, the magnification is just 1. Okay, I got a little example of this. In this example, here I am, and I'm looking down at this shark. I'm at the beach, and I'm looking in the water, and I see a shark. And we're going to figure out the apparent depth below the surface of the water that I see the shark at. By apparent depth below the surface of the water, what I mean is, where does the image of the shark, where is it located at beneath the surface of the water? And we're also going to ask the reverse question: is shark's looking upwards at me, thinking lunch? Shark's looking upwards at me, and how far above the surface of the water does the shark see me? And by that apparent height above the surface of the water, I mean, where does the shark's image of me appear above the surface of the water? And so we're going to figure that out. Now, I should say something about this picture. The rays I've drawn are rays that travel from the shark, get refracted at this surface, so they're bent at this surface. The angle of refraction is different from the angle of incidence, and travel to my eye up here. So the rays I've drawn are the example of me looking at the shark. But there would be rays also I could have drawn, but are not on this sketch, where the shark is looking up at me. Those would be rays that are coming from me and getting refracted at the boundary between air and water and then heading towards the shark. So I've only drawn the rays for one of the two cases that I'm asking the question for. To quantify everything, I'm actually indicating here that the shark is actually, the shark's object position is 0.5 meters below the surface, and my position, my object position for the shark is 0.5 meters above the surface. And then I'm also indicating what the two refractive indices are. So upstairs here is air, which is essentially 1, not quite 1, but and downstairs here is water, which has a refractive index of 1.33. Okay, so where do I see the shark, and where does the shark see me? Well, here's my calculations. This is the calculation for where I see the shark below the surface of the water. That's on the left. This is where the shark sees me above the boundary between the air and the water. I'm just using this equation that we quoted for the image position based on an object position and a single refraction at a flat surface, exactly the situation we got here. So it says that the image position is the object position times this factor, which is minus n2 over n1. We've just got to be careful about who's n2 and who's n1. n2 is the material that the light heads to. It's on the back side of the refraction. N1 is the material that the light originated in. It's the front side of the refractive surface. So when I'm looking at the shark, the light originates in the water, so N1 is the water, and the light goes to the air, so N2 is the air. So I'm plugging in the numerator the refractive index of air, 1, and plugging in the denominator the refractive index of water, that's 1.33. I'm going to get a number that's smaller than 1, which means that the shark is going to appear closer than it actually is. It appears at this location here. The minus sign says it's in, means the image is in the front side of the refractive surface, and it's about 0.37 meters below the surface, so it's closer. I always remember when I do this problem that my mum saying that the water is deep. Everywhere I would go where there's water, the water is deeper than it looks, as if I was going to dive in and drown myself. But anyway, the water is deeper than it looks. The shark is also deeper than it looks, and that's a feature of a single refraction. What about the shark looking at me? The shark looking at me, we're going to figure out my image position based on my object position with the same equation. But we've got to be careful, because now N2 and N1, who's N2 and who's N1 has reversed. Now the light is starting in air and traveling to water. So now N1 is the air, that's where the light starts from, that's the front side, and light is traveling to water, that's the back side, that's where the light is going to. So now I've got the refractive, N2 is the water now, so I've got the refractive index of water divided by N1 is the air now, that's divided by the refractive index of air. So now that's 1.33 over 1, so that's going to be a bigger number than 1, and that means that the my image is located further away from the surface of the water. It's located at 0.67 meters above the surface of the water. Again, that image is on the front side, so it has a negative sign, which says the image is on the front side. Okay. Just to stress this one more time, you know, when the aliens come to invade from outer space, we're looking out from Earth. Here we are on Earth, looking out through our atmosphere. They're closer than they look. So the shark looks out at me, and he sees me, what was it, 0.67 meters away, but actually I'm closer than I look. I'm 0.5 meters away. When we look out through our atmosphere, things are closer than they look. They look further away, but they're actually closer. So the aliens will look further away, but they're actually closer to us. Okay, now let's get on to images formed by two refractions, two bendings, when we've got lenses. Just a little bit of lens terminology or lens language. I kind of summarized it on here. There are two types of curved mirrors, diverging, converging, concave, convex. There's two types of lenses. There's diverging and converging lenses. The converging lenses are the top row here. The diverging lenses are the bottom row here. Converging lenses bend the light towards the optical axis. That's what converge means. It means bend the light towards the optical axis. Diverging lenses are lenses that bend the light away from the optical axis. So they bend the light away from that optical axis. And that's the same as for mirrors, right? Converging, diverging mirrors bend the light towards or away from the optical axis. These two sketches over on the far left, those are the classic. If I wanted to draw the classic converging lens or the classic diverging lens, this is kind of what those two lenses look like. A converging lens is thicker in the middle. A diverging lens is thinner in the middle and thicker at the top and bottom here. So that's what a converging, diverging lens looks like. Look, there's other ways you could make a lens that's thicker in the middle and it converge light. Here's two other examples. There's other ways you can make a lens that's thinner in the middle and it would diverge light, but these are the ones we normally think of. Just like curved mirrors had a personality that was characterized by a single quantity, the focal length. Lenses with these two curved surfaces have a single personality that is characterized by a focal length. And just like mirrors, the lenses have a focal length that has a certain size that's important. It also has a sign, positive or negative, that's important. And I want to show that here. Upstairs on this top row is a picture of light rays in yellow here striking a converging lens. Remember, it's thicker in the middle. And that converging lens will converge the light rays, so bend them towards the optical axis. And here you see these rays bend towards the optical axis, and they pass through this common point here. And if we're shining parallel light rays on the converging lens, then they converge to the focal point. So this is a way of seeing or measuring or experiencing the focal point by shining parallel light rays on it and seeing where they converge to. So here is the focal point. This is the focal distance from the center of the lens. Downstairs here on this bottom row, this is the same sort of picture, but for a diverging lens that bends the light rays away from the optical axis. So here's the diverging lens. It's a little hard to see, but it's thinner in the middle. It's thicker at the top and the bottom. It's going to bend the light rays away from the optical axis because it diverges them. And so you see, here comes the parallel light rays in, again from the left. Here you see light rays heading outwards towards the right. They're bent away from the optical axis. Where do they appear to come from? They appear to come from somewhere over here, right? And if we think about this point where they appear to come from, that's the focal point of the diverging lens. It's on the front side rather than the back side, and that's the kind of personality of the diverging lens. So, moral of this slide is that if you've got a diverging lens or a converging lens, you can shine parallel light rays on it. The easiest way to do that is take it out in the sun. The sun's light rays are parallel light rays when they strike the diverging and the converging lens. And then you can look at where in the converging lens where they appear to converge to, and you've measured the focal length. Or you can, in the diverging case, you can look at where they appear to converge from. Then you've observed the focal length of a diverging lens. There's a formula for the focal length of a lens. Just like actually there was a formula for the focal length of a mirror. The formula for the focal length of the mirror was, I've written it down here, so tiny nobody can see it, but it was really rather simple. The formula for the mirror was that the focal length of the mirror is half the radius of curvature of the mirror. And it was such a simple relation, we didn't even really think of it probably as a formula. But the focal length for a mirror is that it's half the focal length focal length of a mirror is half the radius of curvature of the mirror. It's much more complicated for a lens. The relationship between the focal length of the lens, f for the lens, and the curvature of the lens. The reason it's complicated is probably obvious, right? The lens has two curvatures. There's the front face of the lens and the back face of the lens. The two faces create two refractions. They have two curvatures. So that's going to make the formula more complicated. We've now got an R1 and an R2 because there's two surfaces to the lens. Also with the lens, now you have to worry about two different materials, two different optical materials. You've got like the air in which the light enters from and exits into, and then you've got the material of the lens, like the glass of the lens. So you've got a refractive index. And so this more complicated formula includes all those things. The R1 is the radius of the front surface, the radius of curvature of the front surface. The R2 is the radius of curvature of the back surface. The N is the refractive index of the material of the lens, whether it's plastic or glass or whatever. So this is a complicated formula. It'll be on the formula sheet. Because it's very hard to remember which way round, for example, R1 and R2 are. But it's on the formula sheet. A few comments about it. As I say, R1 and R2 are the two radii of curvature of the two curved surfaces. So that's important. They can be positive and negative. There's a sign convention for that, and you'd be given a table that describes that sign convention. But just to state it, if the radius of curvature of R1 or the radius of curvature of R2 is on the rear side of the lens, that's where the light is going, that's positive curvature. If the radius of curvature of R1 or the radius of curvature of R2 is on the front side of the lens, then that's a negative radius of curvature. So that's the sign convention. So for example, take this lens up here. The radius of curvature of the front side, that's the left-hand side, is over here, somewhere on the back side of the lens, so that's positive. Radius of curvature of the back side of the lens, so this is R2 over here on the right-hand side, that's somewhere over here, that would be a negative radius of curvature. Also, you see the refractive index in this equation. If you make the refractive index bigger, right, you bend the light more. So if we took our glass lens and I made a diamond version of it. Diamond has a bigger refractive index than the glass by quite a bit. That means that light rays would be bent more. That means that the focal length would actually shrink because we more quickly converge or diverge the lens. And this equation says that. The right-hand side gets bigger as the refractive index gets bigger, which means because it's the reciprocal of the focal length on the left-hand side, the focal length will get smaller. So if you could imagine winding up the refractive index, you would be winding down the focal length. You'll be making it shorter and shorter, which means you're more powerful lens, you're converging faster or you're diverging faster. Okay, let's look at a few, the two types of lenses. There's converging and diverging. I'm going to do some ray tracing now, and then I'm going to show you the equations that describe the image's properties, the image location, and the image magnification. So that's the plan. And I'm going to do, I think I've got 2 or 3 slides for converging lens, and then we've got the same slides, 2 or 3 slides for diverging lens. Okay, so this is the ray tracing for the converging lens. This picture here. This time I got the light starting over here on the left-hand side and traveling towards the right-hand side. So for some reason that's unknown to me, the first example with the flat surface, I had the light starting on the right and traveling to the left, but later on in the day I put the light traveling from the left and going towards the right. I'm random, but that's perfectly fine, right? Light could travel either directions. We just got to realize that when we look at the sketch. So that's the first thing. Here's the lens in the center. This is a converging lens, so it's going to converge the light rays. It's thicker in the middle, it's thinner at the edges. Here's the optical axis, the horizontal black line that heads through the center of the lens. So we're friends and familiar with that. On the optical axis, I've marked the focal length. I've marked it over here. This is the distance from the center of the lens. I marked it over here. This is a distance from the center of the lens. I've marked the object position. So maybe we're looking at a fish in a lens. Or maybe I'm looking at a cell or a star in a lens. Here's the object position. Again, I'm representing it as this vertical arrow to indicate its size and its location. And then here I'm telling you this is where the image is going to be located. It's actually on the other side of the lens. It's represented by this arrow here. And the fact that the arrow is upside down means that the image is inverted. It's upside down. And what we want to do is figure out why this image is located here with this inverted kind of shrunken size compared to this object over here. And so we're going to trace some rays. One difference between the mirrors, the curved mirrors, and the focal length there, and the lens, and the focal length there, is that for the mirrors, we only put the focal point on one side of the mirror. It was on the front of the mirror when it was a converging mirror. It was on the back of the mirror when it's a diverging mirror. So we only need to do that to construct the image location. When it's a lens, you actually, because in the lens, the light is on both sides, not just on one side. And for a lens, we put the focal points, and we'll use the focal points on both sides of the lens. So there is a difference here. I've marked the focal points on both sides of the lens, rather than just on one side of the lens for the curved mirrors. So let's trace some rays. I've traced 3 rays in this picture here. And so let me explain those 3 rays and how I trace them. I'm tracing them emerging from the object, passing through the lens. So they're going to get, in general, they're going to get refracted at the lens. And then emerging over here onto the right-hand side where they enter my eye, and my eye sees those rays, my brain interprets those rays and figures out where the image is located. It's where those rays appear to converge to. So we're going to see these rays. Let's start with the black ray here. That black ray just heads towards the center of the lens, and actually just passes, if you head towards the center of the lens, you pass straight through the lens. Now, it's easiest to imagine that if you imagine approaching the lens at the center along the optical axis. Then you would literally strike it at 0 degrees, and you would come out at 0 degrees. So you clearly get undeflected there. But also, if you strike it off the optical axis, although you might get deflected a little bit as you go in to the lens, you get undeflected a little bit as you come out of the lens. So there's no net deflection of this light ray here. So that's the rule for drawing the black light ray. It's the easiest one to draw, right? Just go straight, just remember, it just goes straight through the center of the lens. And it's by going straight through the center of the lens, at the center of the lens, it is obeying the law of refraction. It's important that it obeys the law of refraction at both surfaces. What about the two other rays? The red and the green. They're like the cousins or the brother and sister for the curved mirror. One of them heads in parallel to the optical axis and then emerges through the focal point, which corresponds to it being converged towards the optical axis. The other one heads in to the lens through the focal point and then gets converged by heading out parallel to the optical axis. So blue one is parallel in and through the focal point on the way out, and the red one is through the focal point on the way in and parallel on the way out. So they're the reverses of one another. And I'm just telling you that these rays, these particular rays, have the property that they obey the law, the two refractions. They obey Snell's law of the two surfaces of the lens, and Snell's law says that if you go in parallel, you're going to be bent through the focal point. If you go in through the focal point, you're going to be bent parallel. Anyway, we've got those three rays. They're coming out over on the right-hand side. The eye, my giant brain, is collecting and interpreting. And I say, where do those light rays come from? Where do those light rays appear to come from? I start tracing them back, trace the blue one back, the black one back, the red one back. They appear to come from this common point here. This is where the image is located. And so I have discovered that image is on the backside of the lens. It's a real image. The light rays actually really do come out of this point here. They pass through this point, so that's what we would call a real, not a virtual image. It has some interesting characteristics. Obviously the distance from the lens is interesting, but also the fact that it's been inverted, it's upside down, and it's been shrunk inside. It's smaller than the object was. Anyway, that's ray tracing for a converging lens. This is just the same picture again. And these are the equations that accompany that ray tracing, that support that ray tracing. They tell you exactly what the image position is that you just traced out. They tell you exactly what the image magnification is that you just traced out. So these are the equations that support that ray tracing. The equation that tells you the image position, that's Q, in terms of the object position, that was P, and the particular focal length of the lens you have, is just this equation here, 1 over P plus 1 over Q equals 1 over F. The inverse of P plus the inverse of Q equals the inverse of F. Now, that's interesting. That's exactly the same equation that worked for the curved mirrors. 1 over P plus 1 over Q equals 1 over F. The same equation works for the curved lenses. We'll see it works for converging lenses. We see that it works for diverging lenses. And so we're lucky, we're fortunate. No new equation to recall. The lens equation is the same as the mirror equation. What about magnification? How much bigger or smaller is the image compared to the object? Well, the magnification equation tells you that. The magnification is simply the negative of the ratio of the image position and the object position. You just take the ratio of those two positions, you flip the sign, that tells you the magnification. This equation too, it's not a new equation, we met this equation for the curved mirrors too. The equation for the magnification of the lenses is the same as the equation for the magnification in the case of mirrors. In this case, Q in size is smaller than P, so the image is shrunk, we see that. And in this case, Q is positive because it's on the back side of the lens. P was positive because it's on the front side of the lens, but this minus sign makes the magnification negative. Negative magnification means you've got an inverted image, and this image is inverted. Okay, let me just show you a demonstration of a converging lens. So This is the device, we met it in the last class, here it is, that produces parallel light rays. And I'm going to shine those parallel light rays through some lenses. And I'll show you shining the light rays through a converging lens now, and then we'll look at the case after we do the diverging lens. Light rays shone through a diverging lens. So I'm just pointing that out to you, but I've already pointed that out to you, so no need. But there are 3 parallel rays here. I feel I'm overdoing that. Here's a converging lens. Look, it's thick in the middle and thin at the edges. Actually, this is another converging lens. It's also thick in the middle and thin at the edges, but it's less converging because it's not so dramatic, the extra thickness in the middle, the thinness at the edges. This, on the other hand, is diverging lens. Right? This would, thinner in the middle, thicker at the edges, this will diverge the rays from the optical axis. And just to show you all the toys I've got, this is another diverging one. It's thinner in the middle, it's thicker at the edges. It's not as diverging as the first one, though, because it's not as dramatic, the difference between the thinness and the thickness. Okay. I think I'm going to shut the lights off. Yeah, I shut the lights off so we can see the rays more clearly, and I'm going to plug in here the converging lens. And we stick it in there, and let's take a look. We've got, I'm going to stop this, I think. No, I don't need to stop it. I've got these parallel light rays. They're being bent towards the optical axis. They're converging. They're going through the focal point. So this is indicating the focal point to me. And just to stop it here, you'll notice that there are 2 refractions going on. As we said for a lens, that's an important thing. There's a refraction, a bending of a light ray at the front face and at the back face, and downstairs here. One at the front face and the back face. But the light ray that goes through the center, remember we were drawing this goes through undeflected. And so that just illustrates these different light rays that we tend to draw. Okay. One of the interesting things about converging light ray, and converging lens, and it parallels the converging mirror, is that converging lens, converging mirror, they both depending on the object position, they're both able to magnify and minify, to increase the size of the image and decrease the size of the image. They both actually create virtual and real images. So they both do that. So I have a lot of flexibility with converging lenses to minify, magnify, to make real, to make virtual images, to make upright and inverted images, and that's just like the converging mirror case. I don't think I actually explicitly said that converging lens, like a converging mirror, has a positive focal length. That's the key characteristic that says it's converging. It's a positive focal length. A diverging lens, like a diverging mirror, has a negative focal length. That's the key sign characteristic that says it is diverging. So that's important. Okay, so now let's talk about, where am I going? Diverging lenses. Let's do the ray tracing, and let's do the equations, and then let's quickly do a demo. Okay, so this picture here, ray tracing through a diverging lens, resembles the picture for ray tracing through a converging lens. So I'll go through it a bit more quickly. We've got the lens in the center here. It's thinner in the middle and it's thicker at the edges. That's the nature of a diverging lens. It's the reverse of a converging lens, which was thicker in the middle and thinner at the edges. I got the light starting out over here on the left-hand side and heading towards the right-hand side. So the object is over here on the left. My eye receiving the light rays is over here on the right. Through the center of the lens is the optical axis. I've drawn the image position on the optical axis in green by this vertical arrow. I've drawn the that's the object position. I've drawn the reconstructed the image position in magenta is this small vertical arrow here. And what we want to do is see how that appeared. Why is that image located there? It's on the front side, which actually means it's a virtual image. It's shrunk, and it's at this particular location. Why is that the case? Okay, the other thing I added on here again, these 2 points in gray, this is the focal length of the diverging lens. And again, like the focal length of the converging lens, we're going to put the focal points on both sides, both at that distance, that size of the focal length. Now, in this case, the focal length is a negative number when we do a calculation, but we're still putting the points on either side, just like for the converging lens, we put points on both sides. It was a positive number when we did the calculations using it. And this is a difference between mirrors. Mirrors, you just put the focal point either on one side or the other, depending on whether you're converging or diverging. It's on the front face of the mirror or the back face of the mirror. Okay. We're going to draw the same rays. We're going to draw the same rays. That's the one that goes through the center of the lens, that goes undeflected through the center. And then there's the brother or sister where you go in or out parallel to the optical axis, and the other ray is, in this case, it's not going to be converging through the focal point, but it's going to be diverging away from the focal point. Let's see how that works in this case. So remember, when you're drawing the rays for the diverging lens, you want to make sure that whatever ray you draw, and you try to follow these rules for it, you draw a diverging ray that's bent away from the optical axis. That's the first thing to think about, because it's got to diverge. Likewise, when you're drawing the rays for a converging lens, and using the focal point and all this stuff, following these rules, what you want to make sure is that your rays are converging. They are bent towards the optical axis. That's the first thing to think about. Okay, black ray here goes through the center. It goes undeflected. That's that special ray when undeflected for the converging lens through the center. It goes undeflected for the diverging lens through the center. The other 2 rays, the blue one and the red one. Look, the blue one goes in parallel to the optical axis. The red one comes out parallel to the optical axis. The red one is heading towards this focal point over here on the rear side. The blue one on the rear side of the lens is heading away from this focal point here. This is how we arrange for both these rays to be diverging. Look, the blue ray heads in parallel. It can't head towards this focal point. That would be converging. That would be a converging lens. It must head away, has to head away from this focal point. So it's diverging. So that's why I'm saying be careful about whether you're converging or diverging, because that's going to affect how you draw these brother and sister or cousin rays, the red and blue rays. Likewise, for the red ray to converge, if it's going to come out parallel to the optical axis, it heads towards the other focal point, this one, and then gets bent away from the optical axis and heads out parallel to the optical axis. If I take these 3 rays, and I should have drawn my giant eye and my giant brain even bigger because I've got to collect these 3 rays. I collect these 3 rays, I trace them back to where they appear to come from. So I'm tracing back these red, black, and blue rays. I'm tracing them back through the lens. That's the red dashed lines and the blue dashed lines, and they cross right here. And so this is where my brain thinks the image is. This is an image that's shrunk. It's on the front side of the lens. It's a virtual image. The light really didn't actually come from there. And it's located actually inside the focal length, whereas the object was located outside the focal length. These are the two equations that describe the image properties for this diverging lens situation. And you notice what a relief. What a relief, right? These are the same equations again. So whether it was a converging, diverging mirror, whether it's a converging, diverging lens, it's the same pair of equations that describe the image position, the object position. So you're using the same equations. What you've got to be careful about is the meanings of signs can be different. The meaning of the positive and negative signs of P and Q are different for lenses and mirrors. The meanings of positive and negative focal lengths are different. One means, positive means a converging lens or a converging mirror. Negative means a diverging lens or a diverging mirror. So it's the same equations every time, but the key is understanding that lenses, mirrors, diverging, converging correspond to different signs for the P's, the Q's, and the F's. Anyway, here's the lens equation again. So it would predict the location of this image, Q, if we plugged in the location of the object, P, and the negative focal length of the diverging lens. So the F is negative here. The magnification equation, same equation again. You would plug in the image position, Q, divided by the image object position, P, and the negative of that will give you the magnification. Look, the image position is small compared to the object position. Q is a lot smaller than P, so Q over P is a lot smaller than 1, so the image is shrunk. We can see that. Because the image and the object's positions are both on the front side of the lens, that means P is positive, but Q is negative on the front sides of the lens. So Q over P would be a negative number, but we got an extra minus sign in the equation, which makes this a positive number, which makes the magnification positive, which means that the image is upright, and this image is upright. I'll show you a quick demonstration of the diverging lens, but let me just mention, just like a diverging mirror, it didn't have all those properties of a converging mirror, and the diverging lens doesn't have all the properties of a converging lens in terms of what it can do. Converging lens could magnify and minify. Diverging lens only makes smaller, minifies. A converging lens can make upright and inverted images. A diverging lens will only make upright images. So it's a less flexible lens. Okay, so I'm putting in back in the converging lens, but then I remember that's stupid. I wanted to do the demonstration of the diverging lens, and so I put in the diverging lens now. Look, it's thinner in the middle and thicker at the edges, so this is going to diverge the light rays from the optical axis, and here you can see it. Look. Here's this ray bent away from the optical axis, this ray downstairs bent away from the optical axis. This is that magic ray that goes straight through the center. They all look like they're originating from over here. This would be a negative, this means a negative focal length. And then I think finally I show you the other diverging lens, which was also diverging, but it wasn't as extreme. It wasn't as thin in the middle, wasn't as thick on the edges, which means it doesn't diverge as much. So this ray upstairs here, this ray downstairs, are diverging. They are diverging, but they're diverging less dramatically. So the focal length in this case, you have to imagine extrapolating these light rays back over here. Maybe it's somewhere over here by the calendar. So this is the focal length in that case. Okay, what am I doing? You'll get a table on the exam, like you've got a table on the exam for the mirrors. Table on the exam for the lenses tells you the conventions for the signs of the various quantities in the lens equation, in the magnification equation. Just to give you a few of them. Object position is positive when it's in front of the lens. We said that. It's where the light comes from. Image position is positive if it's on the back side of the lens where the light is going to. So we said that too. Magnification can be positive or negative. That's this line here. If it's positive, the image is upright. If it's negative, the image is inverted. R and R2, those are two radii of curvature in the lens maker's equation. They're signs, they have signs, and it depends on whether their centers of curvature are on the front and back faces. And down here, right, really important point, the focal length has a sign. Converging lenses have a positive focal length, like converging mirrors. Diverging lenses have negative focal length, like a diverging mirror. Okay, I want to end up with at least one example. So we're going to talk about one example. I mean, this is a picture of one example. The eye, right? The eye is will form an image of an object. Eyes form an image of an object. That's how we see things. The eye forms an image of an object by refraction at the outer surface of the eye, the cornea, but also inside the eye is a lens, an adjustable lens, that uses to focus on things, so it also gets refracted there. So light is refracted when it enters through the cornea, refracted some more or some less when it passes through your lens, and then it forms an image on the back of your eye on the retina. And an interesting thing about that image is drawn here. This was like one of the examples, like the converging lens example we looked at. Here's the object, the candle. Here's the image, the candle. It's inverted. So you actually see everything upside down. But your brain's smart enough it turns everything back the other way up. So of course we don't see the room as upside down, but on your retina the room is upside down, but the brain is able to interpret that and put it the right way up. Okay. Thankfully it does that. Okay, quick quiz question. This is a question about a converging lens and a diverging lens. And the question is asking, can the converging lens magnify, make the image bigger than the object? Can a diverging lens magnify, make the image bigger than the object? So, possible answers here are that both of them can magnify, that just converging can magnify, just diverging can magnify. I wish I put, or neither of them could magnify. Maybe that's a possibility, but apparently not. So I'll give you a moment to think about that. I'm going to move on pretty quickly because I really want to do an example illustration. converging lenses, like converging mirrors, can magnify and minify. So they can do both. They're very capable. Diverging lenses, like diverging mirrors, can only minify. They can't magnify. So they're less flexible. So the answer is that it's a converging lens that can magnify. A diverging lens cannot magnify. And the same is true about mirrors. Converging mirrors can magnify. Diverging mirrors can't. Here's an example of a converging lens. A magnifier, a magnifying glass, is a converging lens. It magnifies. Let me just say first of all, how does the magnifier work? The magnifier works by, if you didn't have, these are magnifiers, if I didn't have a magnifying glass and I put something in front of me, and I want to see it in greater and greater in detail, why don't I just move it closer and closer to my eye? Wouldn't that solve the problem? If it was here, I could move it closer, move it closer, move it closer, move it closer, and I'd see it clearer and clearer and see more detail and more detail. The answer is no. The answer is no, because at some point you get to a point called the near point where you can no longer, with your eye, the cornea and the lens in your eye, focus on that object. So when you're young, that's about 25 centimeters away from your eye. So if you try it, you might be able to focus clearly on your finger, right? If you put it 25 centimeters, about 25 centimeters away from your eye. That then is your near point. You can't see more detail about your fingernail by putting it here because it's just a blurred mess, right? At my age, basically the back of the room, the clock at the back of the room is my near point, and that's the first thing I can focus on. Anyway, what the magnifying glass does was it allows you to put something much closer to your eye. It could put something here with the magnifying glass between this object and my eye, and it would create an image of the object which has all the detail, but I can focus on it. So it allows you to focus on things much clearer, much closer than your near point. That's the key thing about magnifier. Okay. So in this problem here, we've got a nickel, here it is, and it's being magnified by a magnifying glass or a magnifier, which is just a converging lens. We're told that the image is located at image position minus 25 centimeters, and the focal length is 5 centimeters, and we've got to find the object position and the magnification. So we're going to do those two things. A couple of remarks about this image position and this focal length. This is a converging lens, so the focal length is positive. So it makes sense that it's plus 5 centimeters. That is a converging lens. The image position, 25 centimeters, we're told is negative 25 centimeters, which means that it's a virtual image and it's on the other side. It's on the front side of the magnifier. So it looks like it's behind the magnifier here. So that's what the minus sign means here. It's not on the side where the light went to, it's on the side where the light appears to go from. That's the meaning of the minus sign there. Because I'm running out of I was going to do this on the document camera, but you know, I'm a very slow writer. I'm going to just do it on the overhead. So, and also I wouldn't be able to draw reliably the ray tracing on the document camera. So we'll just finish up on this slide here. Here's a summary of the information we're told. Image position, Q. 25 centimeters minus sign means that it's on the front side of the lens where the light came from. Focal length It's 5 centimeters, positive 5 centimeters, which means it's a converging lens. Has to be, because it's going to magnify. I can find the object position by the lens equation. The lens equation relates the object and image positions and the focal length. In this particular case, I know the image position, I know the focal length, so I know Q and F. I just don't know the focal point. I don't know the object position P, and so I can solve for the one unknown in that equation, the object position. So I'm going to rearrange this, that the inverse of P is the inverse of focal length less the inverse of the image position, and I'm going to just plug in the focal length. It's 5 centimeters, so 1 over 5 centimeters is 0.2 inverse centimeters. I'm going to plug in the image position. I'm plugging in minus 25 centimeters, so minus 20, the inverse of minus 25 centimeters is minus 0.04 inverse centimeters. Then I'm going to subtract I'm going to add. I've got to be careful about the signs. So there's 2 minus signs here, so I'm going to end up adding to the 0.2 inverse centimeters, the 0.04 inverse centimeters, which is going to give me 0.24 inverse centimeters, and then I'm going to take the inverse of that to get the image object position. It comes out to be 4.2 centimeters. When you use a magnifier, best way to use a magnifier is to put the object that you want to magnify just inside the focal length. So this magnifier had a focal length, we were told, of 5 centimeters. So if you've got a magnifier, put the object just inside that. And 4.2 centimeters is just inside the 5 centimeters. That's how you create a magnified image. So we've used the magnifier in a way to magnify by putting the object just inside the focal length. The object position was 4.2 centimeters, the focal length was 5 centimeters. We made a magnified image at 25 centimeters away, which means that we can actually focus on it. We couldn't focus on the object because it was too close to our eye, but by putting the image further away and enlarged, we can focus on it and we can see all the details of the penny or the nickel or whatever it was. Okay, magnification. Magnification is just the negative for the ratio of the image position and the object position. And the object and image positions, we now know both of them, so I've just got to divide negative 24 centimeters by positive 4.17 centimeters. The number is 5.8. We got 2 minus signs here. Minus sign associated with the value of the image position, which was negative, and the minus sign in the equation. So we end up with a positive sign, which means that the image is upright. It's the right way up. Here's the picture. Here's the ray tracing diagram that describes this image formation. Look. Here's the lens, here's in horizontal, the optical axis. I marked the focal points. I've drawn 3 rays. The ray that goes through the center in green, the brother and sister or cousin rays that either head in parallel to the optical axis or head out parallel to the optical axis. I've drawn those rays. I imagine my eye over here, reconstructing where those rays appear to come from. And we reconstruct by tracing these rays back through the dashed lines to an image being located here. Look, it is further behind the lens than on the front side. It's further away than the object originally was. It's at 25 centimeters away rather than 4.2 centimeters away. And it is enlarged. And we can see all the details. We can focus on all the details. Anyway, that's an example as a magnifier. I put in let me just say a few words. I put in 2 slides on a telescope and a microscope. The intent was not that you understand the details of a telescope and a microscope. I just wanted to say that what are telescopes and microscopes? They add 1 extra lens to the magnifier. It's a lens called the objective, and the objective actually just means something in front of something else. So they put one lens in front of the magnifier. The purpose of the one lens in front of the magnifier is if you're looking at the moon with a telescope, that first lens, the objective, just puts the image of the moon at this location near the focal length of the magnifier, and so you magnify it. If you're using a microscope, the objective of the microscope, if you're looking at a cell, it just puts that objective lens, just puts the image of the cell at this location near the focal